Hey there, it's Shannon Math Chick Myers, and now we're on the second portion of 5.1, which is looking at modeling linear differential equations with constant coefficients, and we're moving on to spring mass systems with free damped motion. So, free harmonic motion is a bit unrealistic, fun as it is, since the equation m times that second derivative of x with respect to t equal to negative kx assumes that there are no forces acting on the moving mass. Unless the mass is suspended in a perfect vacuum, there must be at least a resisting force due to the surrounding medium. So this is kind of, very not professional sketches of what a system with undamped motion would look like. So actually move this down a little bit. And I might as well copy it over here. All right, so the first one has our spring. So remember, it's like mounted on something or other. And then you've got your spring, which is coming into some kind of liquid. So if we just have, this liquid here, that's some kind of purple liquid. So our spring is going to come in here into the liquid, and that mass, of course, will be attached to it. So I'll just make a little box for the mass. M for mass. Cool. And then the other one that we're going to discuss is, what if you had some sort of cap on it? So here's the edge of the water. And so there's this surface that the spring is pushing down into this system here. So then you would have your something connected, of course, to the spring. So let's just say you had something like this connected to push this deal down. And then you've got the spring hooked up here. And the mass is going to be somewhere around here. And that spring will connect to the mass. Groovy? All right. And put M for mass right here. So a little bit different than before, but that's okay. Gives us something exciting to learn. Damping forces acting on a body are proportional to a power of the instantaneous velocity. Therefore, the force is given by a constant multiple of dx dt, that first derivative of x with respect to t. Assuming no other forces are acting on the system, Newton's second law gives us the mass times that second derivative of x with respect to t, negative kx, which was part of the equation in 5.1.1. But now we're going to subtract some constant beta times dx dt. Now, beta is a positive damping constant, and the negative sign is due to the fact that the damping force acts in a direction opposite to the motion. So, all right, let's see what we have. We have m times this second derivative of x with respect to t is equal to negative kx, just what we wrote before, minus beta times dx dt. And then let's go ahead and put it all on the same side of the equation. And so we'll have m times second derivative of x with respect to t plus k, and we're going to put that derivative in the middle there, plus beta times dx dt, and then plus kx is equal to 0. So this is linear, a linear dE. That is homogeneous, right? Now, here we go. If we divide through by m, or multiply through by 1 over m on each side, then we're going to end up with the second derivative of x with respect to t plus beta over m times the first derivative of x with respect to t plus k over m times x is equal to 0. Now, we're going to let 2 lambda, again, this is going to be for ease of solving the quadratic equation. So 2 lambda is going to be equal to beta over m, and omega squared, if you recall from the last little section, is equal to k over m. So we'll rewrite this equation with lambda and omega. And then we need to find our auxiliary equation, which of course is m squared plus 2 lambda m plus omega squared equals 0. Cool so far? All right. And now let's use that quadratic formula. So m will equal to, the coefficient to the m term is 2 lambda. So the opposite of 2 lambda, plus or minus the square root of 2 lambda squared minus 4 times 1 times omega squared all over 2 times 1. And that's just using our quadratic formula. Continuing, we will have m equals negative 2 lambda plus or minus the square root of. We're going to have 4 lambda squared minus 4 omega squared. So we factor out that 4. we'll get lambda squared minus omega squared all over 2. So then m will be negative 2 lambda plus or minus 2, bringing out that, because 2 squared is 4, right? And then we'll have times the square root of lambda squared minus omega squared all over 2. So reducing, we'll get m1 is equal to lambda plus the square root of lambda squared minus omega squared. And sorry, that's a negative lambda. And then m2 will be negative lambda minus the square root of lambda squared minus omega squared. Cool, cool? All right. Now our differential equation is going to depend on what kind of quantity we get when we subtract omega squared from lambda squared. So, of course, there will be 3 cases. Looking at case 1, where we have lambda squared minus omega squared is positive, the system is overdamped because the damping coefficient beta is large when compared to the spring constant K. And then what'll happen is we'll get x at t is equal to, now remember when we do this one, we end up factoring out an e to the negative lambda t, and then we're going to have the quantity c1 e to the square root of lambda squared minus omega squared plus c2 times e raised to the negative root lambda squared minus omega squared. And this is all from techniques we learned in chapter 4. And the kind of motion that we'll get with this system is smooth and non-oscillatory motion. So it's going to look something like this. So t would be on the horizontal, x would be on the vertical, and then there's a couple of pictures that it could look like. You could have something that looks like this. You could also have something that looked more like this. And remember, and this represents smooth and non-oscillatory motion. Now case 2, when lambda squared minus omega squared equals 0. This system is considered critically damped. Because any slight decrease in the damping force would result in oscillatory motion, which we don't want. So you have x at t is equal to e to the negative lambda t, and then we get c1 plus c2 times t. We'll have a multiplicity of 2 for our result. All right, so what does this look like? Well, this one will have a curve something like this. Or it could go something like this. Again, this one was for critically damped. Okay, now what if you get a negative in that discriminant? So when lambda squared minus omega squared is negative, the system is considered to be underdamped. since the damping coefficient is small in comparison to the spring constant, the two roots are now complex. So what will happen is we would end up getting m1 equals negative lambda plus the square root of omega squared minus lambda squared times I. M2 would be negative lambda minus the square root of omega squared minus lambda squared I. This will give us x at t is equal to e to the negative lambda t, the negative lambda is like our alpha, and then we'll get c1 cosine of the square root of omega squared minus lambda squared times t plus c2 times sine at the square root of omega squared minus lambda squared times t. What does this one look like? We'll have a comparison on this one. So here's our x-axis, and here's our time axis. And so an undamped system is periodic, right? So an undamped system might look something like this, right? And so this would be undamped. And then underdamped will look like something that has that's kind of wavering, getting closer and closer to that line T. Cool, cool? All right, and now we're on our example. All right, so here we go. A 4-foot spring measures 8 feet long after a mass weighing 8 pounds is attached to it. The medium through which the mass moves offers a damping force numerically equal to the square root of 2 times the instantaneous velocity. Find the equation of motion if the mass is initially released from the equilibrium position with a downward velocity of 5 feet per second. Find the time at which the mass attains its extreme displacement from the equilibrium position. What is the position of the mass at this instant? All right, so here we go. What is the mass? Beautiful. M equals 8 pounds. Now, you got to be careful here because we're going to end up having to change that into a slug, all right? So the weight, remember, is M times G. Well, we're in feet, so that's going to be 8 over 32 equals 1/4, and that's a slug. Isn't that a lovely name? A quarter slug. Cool, cool? All right, and then, well, let's look at K. So we're going to have 8 is equal to K, and then what is the S going to be? So it's a 4-foot spring, but it measures 8 feet long after this mass is attached. So remember that when it comes to rest, to equilibrium, it's 8 feet long. And the spring started at 4 feet long, and so it's going to be, S is going to be 4, because 8 minus 4 is 4. Groovy? Okay. So that means that K is going to be 2. And that would be pounds per foot. All right, so let's take a look at what we've, come up with here. So what will our equation look like? So we've got 1/4 slug times that second derivative of x with respect to t. And then the damping force, right, is equal to what? Beautiful. Root 2 times the instantaneous velocity. So we're going to have plus root 2 times dx dt, which is the instantaneous velocity of x with respect to t. And then now we know that k is 2 from over here. And we'll have 2 times x, and all that's equal to 0. Isn't that groovy? Now, multiplying everything by 4 so that we can get a 1 as a coefficient in front of the second derivative. We will have 4 root 2 times dx dt plus 8x, and that's still equal to 0. Now we can get our auxiliary equation, which is m squared plus 4 root 2 m plus 8 is equal to 0. I know it looks ugly, but it's okay. M will equal to, using that quadratic formula, the opposite of 4 root 2 plus or minus the square root of 4 root 2 squared minus 4 times 1 times 8 all over 2 times 1. So we'll get m equals negative 4 root 2 plus or minus the square root of, that's going to be 16 times 2 is 32 minus 32. So we'll have one with the multiplicity, right? So now m will just, so m1 we'll say is equal to negative 2 root 2 with multiplicity of 2. And so that will be the case where we will have x at t equals c1 e to the negative 2 root 2 t plus c2 t e to the negative 2 root 2 t. Cool so far? And then cleaning it up a little bit, x at t would be e to the negative 2 root 2 times t. And then we'll get c1 plus c2 times t. Groovy? Now, let's think about what we know, right? So at time 0, what is the displacement? It's at equilibrium, right? So at time 0, it's 0. So that means that for x at 0, we'll put in 0. E to the negative 2 root 2 times 0 times c1 plus c2 times 0. And so what will we get? 0 equals, this will be 1, and we'll just have c1 plus 0. And so c1 is equal to 0. All right, now let's find x prime at t. So x prime at t will be negative 2 root 2 e to the negative 2 root 2 t times c1 plus c2t, and then plus e to the negative 2 root 2t times the derivative of what's inside, which will just be c2. And so cleaning it up, let's see, remember that c1 is 0, right? And so it looks like we can go ahead and write x prime at t as e to the negative 2 root 2t times negative 2 root 2 c2 times t plus c2. I'll just leave it like that. Now, what was the initial velocity? It's downward, right? So remember, downward velocity is positive and it's 5 feet per second. So 5 is equal to e to the negative 2 root 2 times 0 times the quantity negative 2 root 2 c2 times 0 plus c2. And so that's going to give us 5 is equal to, what's that going to be, 1 c2. So let's see what we've got shaken, okay? So this has given us that x at t is equal to, so c1 is 0, c2 is 5, so we're going to get 5t times e to the negative 2 root 2t. Cool so far? And x prime at t will now be equal to 5 e to the negative 2 root 2 times 1 minus 2 root 2 times t. Cool, cool? All right, now if we set that derivative equal to 0 and solve, then we'll get our critical number for t, right? So here we go, setting x prime equal to 0 and solving. Notice that the 5e to the negative 2 root 2t is never 0. So we'll be focusing on 1 minus 2 root 2 times t. So 0 equal to 1 minus 2 root 2 times t. We'll get 2 root 2t is equal to 1. T is equal to 1 over 2 root 2. But if I rationalize that, I think it's going to clean it up quite a bit. And so that would end up being what? Root 2 over 4. And that's root 2 over 4 of a second. Cool so far? So that's when extreme displacement will happen. Good so far? And so let's see what we've found. Okay, we found the equation of motion. Okay, so the equation of motion is x at t. Okay? And then find the time at which the mass attains the extreme displacement. So that was this one here that we just found. And now we need to find the position. So to find the position, what do you think we should do? Beautiful. Let's evaluate x at t at root 2 over 4 of a second. So x at root 2 over 4 will equal to 5 times root 2 over 4 times e to the negative 2 root 2 times root 2 over 4. So x at root 2 over 4 equals 5 root 2 over 4 times e to the, let's see, root 2 times root 2 is 2. So it's just going to be negative 1. So that will be in feet. So position of the mass at that instant. Position of the mass exactly when t equals root 2 over 4 of a second is 5 root 2 over 4 times e to the negative 1 feet. Groovy? And that is our last thing we had to find. All right, so here we go. I think that the next step is alternative forms of x at t. So here we are. We learned a bit more about this in that last little subsection. So we have x at t can also be equal to e to the negative lambda t times c1. This is what we started with, okay? Cosine of the square root of omega squared minus lambda squared t plus c2 times sine at the square root of omega squared minus lambda squared t. So the alternative form is x at t equals to a e to the negative lambda t times sine at the square root of omega squared minus lambda squared t plus phi. And they are the same as we had before. So basically, a, remember, was equal to the square root of c1 squared plus c2 squared. And then sine phi is equal to c1 over the square root. Actually, I'm just going to write a. It'll be less messy. c1 over a cosine phi is c2 over a, and tangent phi is equal to c1 over c2. Now the coefficient a, e to the negative lambda t is called the damped amplitude of vibrations. Since this alternative form of the equation is not a periodic function, the number 2 pi over the square root of omega squared minus lambda squared is called the quasi-period, and the square root of omega squared minus lambda squared over 2 pi is the quasi-frequency. The quasi-period is the time interval between two successive maxima at x at t, or of x at t. All right, and that wraps it up for the second little subsection. So I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, click that subscribe button and hit like. Bye.